this point. But tomorrow morning, probably around 9 o'clock, or probably really not a time change, about 10 or 11 o'clock this time tomorrow, we should be up to about full testing. So this has real heat pipes and real Stirlings. We only got 2 Stirlings because NASA was cheap and couldn't afford all 8, so we got 6 simulators, 2 real Stirlings. We will make real electricity. Each Stirling will make a little over 100 watts, about 120 watts each.
So I was wondering, after this reactor turns on and it's 1 watt, is there any likelihood it loses its coal rod that will have a Chernobyl effect?
So it's going to be hard for the reactor. I told you it has a real, what's called a negative, really strong negative temperature feedback coefficient. So again, you know, what happens is that as the reactor heats up, that inserts lots of negative reactivity. So basically it will match the power load that it sees. So one of the experiments we're going to run is we're going to turn off all coolant. Well, it'll be already out all the way anyway because it'll be at full power, but we're going to turn off all coolant. The reactor's going to go down to about 100 watts of power generation because that's about the residual heat loss, and it's going to sit there and be very happy. So another thing that makes this reactor very safe is its power density is super low. So it's got a power density of about 1 watt per cc. A normal power reactor is up around 100 to 400 watts per cc. So what it means is that I don't really get, you know, like in a Chernobyl, not Chernobyl, so that was a power spike. But if you think about Fukushima, it really couldn't reject the decay heat. It really, those type of reactors have a hard time rejecting decay heat and doing lots of other things. And this reactor is so small that really we're not going to have trouble just radiating the heat away. So no, it'll just sit there as a block of metal and it'll be hot, but it'll be happy. I don't know, I got 2 more.
So can you compare your reactor concept to other nuclear generators that have gone on deep space probes such as the Voyagers?
So the real difference is most of those are radioisotopes. So they're not reactors, they don't fission. They use decay heat, right? So we get plutonium-238, which really has a lot of decay heat per watts per gram. Now they have a lot of radioactivity in them, but again, they're not fissioning. It's just a fission product. They package those real robustly, which makes them super safe. But they're on all the time, right? And basically, they'll produce enough energy that we hook thermal electrics up to them, and they get you about 100 watts per unit. But Voyager's great because they last a long time, right? In this case, Voyager's been going 30 plus years, whatever it is, and they're pretty simple.
Do you know what the Curie load was on Voyager?
So Voyagers were about 60,000 Curies each. Yeah, and we're about, like I said, we're about 2. So, give you kind of an idea. Yes, sir.
How many years would a 10 kilowatt reactor produce power?
Good question. We tell NASA about anywhere about like 10, we're telling them 5 to 15 years depending on what they decide to do with it. Reality is the reactor's never going to run out of power. It's going to go, our what's known as burnup, how much U-235 we fission is trivial. Something else will break first. We expect the Stirlings to break first. What's going to happen is slowly over time as it fissions U-235, the temperature will start to drop slightly, not much, 10, 15 degrees. So over time, eventually, it would lose enough energy that the Stirlings wouldn't work, but that'd be a really, really long time down the road. It's a tremendous waste of uranium, by the way, but we really don't care. Okay, I'm gonna go to someone in the back here.
Have you thought about the disposition path for the waste after the reactor has got to its end of its life? What happens to that?
So, good question is what do we do with the reactor when we're done? So I can tell you what NASA's planning to do. They're not going to bring it back, mostly because it takes a lot of rocket energy, and I don't think we're there yet. So they have these big storage lockers. We're going to shut them down. And I've seen pictures of them. They actually get stored. A lot of stuff gets stored if we end up going to Mars. Believe it or not, human waste and a lot of other things will get stored to such a time when they think they could dispose of it. So at least that's right now what I've been told. Yes, sir.
The Stirling generators. So there was a previous
thermal generators that using the Stirling?
Correct.
Are these the same Stirling generators that they developed for those?
Good question. The answer is yes, but we're not going to for long. The reason we did is because there was a project to put Stirlings to radioisotope systems. They spent a lot of money on those, about $1 million each. We got those for free. So for our project, it was great. So that's what we're using right now in our test. To be honest, none of us like those because they tried to be really fancy. They tried to make them super high efficiency and really low weight. In a lot of ways, to me, they cut the reliability on it when they did that. So my goal would be to go back to one that's a little clunkier. I don't care it has so much efficiency, and I would take more weight if it were just more reliable. And they have those, so I'd like to switch out. But I'll be honest with you, it won't be my call anyway. It'll be nasty, since that's their thing. Yes, ma'am.
So we don't really here at the lab have a lot to do with the Stirling engine aspect of this.
We do not.
But is it something that we might like to get into with the materials work that we do to try and improve on what a Stirling engine does?
To be honest, there's a lot of industry that's doing this.
Oh.
So you guys probably don't know it, but there's tons of manufacturers that make Stirling engines, and the opposite of a Stirling engine is a cryo cooler. You can do that as well if you go the opposite way to do refrigeration. And there's a lot of commercial companies that do that. Right now they're moving to a thing called an acoustic Stirling. And again, there are a lot of commercial people doing that. So honestly, I think from our perspective, they're kind of out in front of us. I would think our role is, it's kind of like heat pipes. We still build heat pipes for very unique applications, but they're ubiquitous. I mean, if you've got a laptop, it's got heat pipes in it. Yeah. So, yes, sir.
How much power is the Mars base in a wall?
So they're telling us 40 kilowatts. That means we're not going to send 4 reactors.